Okay, let me start. Thank you to be here for this lecture. We will try to, I will try to show you an interesting application, two applications, I would like to say, in robotics. But in particular, we will go in depth in one application. And the second one, uh, we will sketch. We will sketch for different reasons. Uh, because it's extremely complicated. Also, in Zoom, it's not so easy. In particular, when I will show you the implementation of Simulink MATLAB in the first application, which is a little bit more intuitive, and not only consist of, I would like to say, a straightforward, even though straightforward is not a system. But nevertheless, the second example should be useful in order to see a little bit more the application, even though I don't want to be boring with calculations and the implementation. It's in particular in Zoom extremely heavy, but you can really understand the method and also the possible application in Simulink MATLAB with the first step for the application in real world. The second example is the segue. I will tell you a little bit later in detail, which you can see also in some seating. For instance, here in Lüneburg, you put €1 in this Segway, you can travel, I don't know how long. This is the example, the final example, which I will present, but without insisting too much in mathematical aspects, even though we will consider nevertheless some calculations. And I would like to avoid the implementation in Simulink because we will see that also in an easy example is relatively heavy to be explained and to show also with the simulation. But the first example I will present. Now, let me start with a preliminary presentation very quickly. Let me share now the presentation in order to introduce, I think you can see the slides which you have in order to introduce elements of robotics very quickly, in order to introduce the nomenclature, in order to introduce the basic laws, in order to introduce approaches, possible, I would like to say, ideas to model at the beginning. Nomenclature, dynamics of robots. The dynamics consider forces and torques in the description of the robot. Probably, excuse me. You know, and you have seen also in the description of mechanisms, robots, between mechanisms and robots, in system theory, we don't distinguish because for us it's in the system. As I told you, I am working with population dynamics. I'm working with economical systems. For us, they are systems. But of course, we have also the possible definition, nomenclature, but I don't want to go here in depth on this. We will see what a robot is. Let me say practical in the sense with an example. Um, I remember in a comedy in theater, in which I remember Chekhov, which says the difference between a human and a robot is the robots or a robot is never tired. This could be also a nice definition. I mean, they repeat movement as a human, or they repeat motion. We will see what the motion, how, what an emotion is, infinite times without being tired and without being bored, of course. But let me go a little bit more in depth on this definition. Forces and torques. This implies the dynamics or the dynamic the dynamics of a robot is characterized by the acceleration. The acceleration, we will see, is the relevant variable, let me say so, roughly speaking, of the dynamics. Because we can describe the movement, the motion of a robot using just kinematical variables, position, velocity. In this case, the forces of the torques must be compensated, should be a zero in this sense. And the acceleration, linear acceleration or angular acceleration, also zero. This means does not appear, we don't consider in the motion. The word which I already introduced, motion. The motion is the key point of a robot. I mean, motion means, let me say, roughly speaking, movements. In order to describe the movements in terms of dynamics, of course, we need forces, as I told you, or torques. And we will see that extremely important is the model for different reasons. First of all, for control, we will see today, because the lab is concentrated, I would like to say, on control. The reason is, lab is an application. And as I told you at the beginning, a robot and mechanisms, in general, a system without controlling, we cannot use, we cannot apply. Therefore, I thought to tell you, to introduce, to stress the part of the control. It's extremely important for the control. This does not mean that we cannot control a robot without knowing its model. It is possible, but it's not so effective. Typically, we don't do. We have to have the model, or at least nowadays, for differences we will see during the lecture. Yeah, this is the reason why I insist on the model. But not only, the system is so complex. It's so complex that in order to observe, in order to predict, in order to monitor all possible movements and all possible states, we will see the keyword, extremely important keyword, states. We need a model. We need a model. Otherwise, we cannot, I don't want to say control again, well, we cannot monitor everything which happens or everything which could happen during the movement, during the motion. And the motion is our goal. We can move or we can stay with the robots, or with the robot, if you have one, or some part of the robot. Yeah. Equation of motions, let me say, arises, the equation of motion arises from torques on forces. This is they are our causes, which is generated by actuators. I will clarify in a few minutes what I intend, which is applied to our mechanism, for instance, a manipulator. A few words about nomenclature, which we will use in the examples. Theta, theta dot, their position, velocity, and acceleration. Quite abstract this moment. Tau, typically, with tau we indicate forces and torques. Could be our causes, our inputs, let me say, can be force or forces, and can be torque or the torques. Yeah. We have basically two possible approaches: Lagrange approach and Newton approach. In some books, Lagrange Euler, Newton Euler. We will see today the Newton approach, because basically the example which I would like to present, or the examples, is not so difficult to be approached with Newtons. And probably you know already Newton somehow. from high school, from different courses, in accordance with with the time which I have to invest in this lecture, I think is more appropriate. Even though sometimes I would like to say is more here is I put messy. mm, it's more difficult, I would like to say. But if the system is not so complex, in accordance with your pre-knowledge, in my opinion, we can understand better. But in any case, I don't have time to look at to present the Lagrange method. But moreover, you will, in different courses, you will consider the Lagrange method as an energetical method, no? Energy-based method. Kinetic energy, potential energy, and so on, or different energies depends of the system which what we are considering. I will tell you later a little bit better. In Newton, we have forces or the torques. Torques can be seen, can be the name of torque. We can say in equivalent way momentum, no? Or the momenti. In both cases, we can build models. We can build models. Let me show. Quite general, quickly. The first equation is a state space equation. We will see in detail with the examples, which we can see that forces and torque, let me consider just torque, equals three elements. We can see the first element, which is the inertia matrix. In our case, we will see in our easy example, we will see also the matrix too. But in any case, if the articulated system is the robot is easy, sometimes we collapse it in scalars. No? But very interesting that this inertial matrix, this M, which is the matrix which characterizes the inertia of the system, is a function of theta. It's a function of the, if you think theta is in a position, in particular, for instance, in this case, is an angular position, makes sense because if you think, we will see later also, an articulated, exactly what I will present in a few minutes, yeah, later. The position, if you think about an arm of a robot fixed on this joint here, this here, the inertia is different if in this position, in this position, on this position. I will come back in a few minutes. This is something which can be considered in general, even though I don't have time to go in depth. That I would like to give you this information here. This centrifugal and Coriolis terms, yeah, this is also present in system complex in which we have a complex movement. This means in which we have the coexistence. We have two basically movement and translation and rotation together. Probably you have seen in physics or in technical mechanics this element here, centrifugal Coriolis terms. G, this is a function of position and velocity also. G theta is in the gravity terms. Also, the gravity terms, why is it a function of theta? Because if you think again on the system here and this position here, the gravity is completely in this angular position, we will see in detail later, is completely compensated by the joint. Think about intuitively. I don't have time to go in depth with really complex articulated system because the idea is concentrate on the control. Look at this. But to control, as I told you, we need a model. Look at this example here. We have a force, we have a mass M1, we have a mass S2. Then we have, let me say, spring effect, damping effect between or among the elements which we see. Typically, we oriented the system with two orientation means two things. We can orient in terms of input output. Example, F input, F of t, the force. And the output, I can choose x1, I can choose x2, I can choose both. I can choose x1 and x1 derivative, position, and velocity of the mass m1. But I can do the same. I can monitor, I can orient it f and x2 and x2 derivative, or I can consider more than two output to be monitored or to be controlled. This is the first concept, or what we intend with the word orientation of a system. Oriented input output, or the inputs plural. In this case, we have just one, outputs plural. But orienting means also orient where, which positive direction I have the input, which seems to be oriented graphically, at least, from left to right. And also we can consider how orient the movement of M1 and M2, of the mass M1 and M2. It seems to be also oriented from left to right. Typically, we can choose whatever positive orientation, but typically we orient everything in the same way in order to be able to model in a more easy way. Of course, the direction in right, from right to left for x1 and x2 and for their derivative. Here, let me show you how we can build the Newton model, which we will use also later in more practical example, in the example which I would like to simulate with Simulink. We can see on the left part as the model consists of basically three forces. Everything is inspired by this expression here, in which we have that m1, in this case, m1 multiply the acceleration of x1, this means x1 dot dot, equals the sum of the forces acting on the mass m1. And we have a friction force, the spring force, inertia force, characterized by the damping factor D for the friction force, the stiffness factor K, or spring factor multiplied X, and the inertial force is characterized by the mass as a constant. Of course, the mass is multiplied by the acceleration to obtain or to describe the inertial force. K, this stiffness is multiplied by the position to characterize the spring of force, and the spring, again, K multiply X characterizes the spring force. We have to be careful with the, with the wording. And the friction force is characterized by D multiply X derivative. Basically, the velocity is proportional to the velocity. Of course, these three, and in particular, the friction force and the spring forces, are possible models, but not the unique one. I will insist a little bit later on this concept here, and in particular on the friction force, because the friction force is in robotics and mechanisms, is really in a big chapter of modeling also for the control. The reason is that it's not what we see is really in a simplification of the friction force. This model here, the model of the friction force, is just a linear model, which, for instance, does not consider the static friction, but not only. The friction model could also include, why not, the parameter which multiply the velocity square, multiply by a particular function, which is the sign of the velocity, in order to maintain the direction against the movement. Also, the spring could be a more complicated model, not necessarily a linear model. But let me remain on this two model, because otherwise we will see that the model will be a little bit more complicated. But in any case, I would like to sketch what I intend for a nonlinear friction force very quickly, because I told you that, one second, that the model could be really, really different. In particular, if the friction model is modeled a little bit more realistically, what I intend is this. FD, I don't remember the notation. Let me see. FD. In general, no? X1, X2, the velocity is a linear function. No? But this is really something which not necessarily represent the reality. For instance, let me consider this. Which is quite different. Now I will clarify what this is. Hmm? In which we are considering the static friction. Why SGN? Why SGN? SGN of x derivative is a function defined one if x derivative is positive, zero if x derivative is zero, minus one if x derivative is less than zero. Basically, is the sign of the velocity. Why is there? Is there because SGN is there this SGN in order to guarantee that the friction is always, or the force of the friction force is always against the movement, always against the velocity. In some books, we find with minus, no? But you can consider minus in the equation. Of course, I can consider also another term. Why not? I mean, this is the Coulomb, let me say, expression of the friction. But we have different model, Lou-Gray model, many others. What is this model here? In which we have the quadratic component, meaning as long the resulting force is here inside, we don't move. Velocity zero. Exactly what I am experiment, for instance, here. Of course, this is probably the weight of this. The weight of this is does not allow us to remark or to notice this effect. But if you consider this table, if I try to move the table, of course, as long as I don't overcome this force here or this force here, depending on the direction I do move. But anyway, just to be complete, similar consideration can be done also for the spring forces or the force. But let me go ahead with the model because it's not exactly the topic of today, but just to sketch, because it could be that you will find some possible considerations in your different courses. Look at this balance here, extremely important for today. We will see in the example which I will present. F of t, let me say input or motoric force minus three elements. As I told you, the force which is working again because of the presence of a spring, the force which is working again of the presence of the damping factor, and we have here a force Fd12, which is an interconnected force between the mass m1 and the mass m2. At this moment, we don't know what is. Similar consideration can be done for the mass too. The difference here, that here, we don't have the inputs. We don't have the inputs. It's clear. We have probably different spring parameter or damping parameter, but the balance is the same. But look, if FD12 has this direction, can be fixed arbitrarily. We have an equivalent FD12, but with opposite direction. This is intuitive, can be also explained physically a little bit more in depth, but of course, in between, we have a reaction which is, let me say, equals but opposite. I don't know if you remember this sentence in physics. Now, the unit thing which must be defined is exactly this FD12. FD12. We can see this minus FD12, excuse me, here plus FD12 equals but opposite. Probably you remember in the lecture of physics this concept here. Let me go ahead because it's not exactly in a lecture in physics, but we can understand what I intend. Here's a little bit the idea to characterize this force which is equal but opposite. In order to understand better, probably I would like to come back here because it's I copied this material from a book. Look at this. If I move left the mass m1, assuming that I fix m2, I have the reaction. Let me say the reaction on the mass m1 in accordance with the friction force is minus d12, which multiply x1 derivative in accordance with the model which is here. Because m2 does not move, but if m2 will move, of course, I have to consider the difference between the two velocity. Because if they move with the same velocity, we don't have a reaction in between. Assuming the linear model, then the reaction on the movement of m1 is minus d12 parenthesis, which multiply x1 minus x1 derivative minus x2 derivative, parenthesis. And this is a little bit what I will try to explain here, is exactly here, no? Minus d12, which multiply x1 derivative minus x2 derivative. Or, if you want, plus d12, which multiply, in parentheses, of course, x2 derivative minus x1 derivative. We can see that basically fd12 is the same. If you put in evidence a minus here, it's basically the same, but inside the equations, one is what with plus and one is what minus. Because they are equal but opposite in the balance. In the balance. Equal is opposite in the balance. I don't want to insist because probably you know better than me this physical concept. But anyway, now I plug in what I try to explain quickly. I will have these two equations, the two equations, dynamic equations, because we are considering the acceleration. Again, do remember, because of the presence in this case just of a force, we will see in our case we have the torque, and then also together with the force in the second example. But very important is the effect of this force, in this case, is the acceleration. And we can see that the acceleration plays plays an important role in the balance, but in particular in the last four equations, in which we can see explicitly that the acceleration x1 is equal something which really characterizes the system, and the acceleration x2 equals something which characterize, let me say, x1 derivative, x1 dot dot is characterized by, let me say, the element of the acting on the mass m1, we can see here. And the acceleration x2 is characterized by the elements acting on the mass m2. Please pay attention, F is acting on the mass m1. These two equations are kinematic equation, nevertheless, is there in order to complete the representation. The derivative of the position equal the velocity, the derivative of the position of mass 1, x1 derivative equals the velocity, the derivative of x2 equal v2. This means the derivative of the position of the mass 2 equal the velocity of the mass 2. I will reorganize everything in this form. Very often we will see in the book first two equations characterize the mass m1, let me see. Second two equations characterize the mass m2 in terms of position, velocity, and in particular acceleration. From here to here, the system is linear. I don't need to really to explain many things here. But we can see that I can compact this information here in the upper part of the slide in this form here, which we have the state variables. We will see in detail what I intend for the state variables in the example in a few minutes, which is equal the matrix multiply, or better to say, here's the derivative of the state matrix, excuse me. And on the left, the derivative of the state matrix equals the matrix, which we can see here, which multiply the state. The state is position, velocity of mass m1 and the mass f2. Yeah, today we will see that the system is nonlinear because it's more general. This means we will not use this possible representation using matrices. But I think you know already how we can express a dynamical system using matrices. No? This means row multiply column, I will get exactly this information here. Row multiply column, I will get exactly the dynamics, let me say, of the mass m1, and so on. This is a typical representation of a linear system using matrix and vector. Again, the derivative of the state variables, we will see the meaning of state, equals the matrix which multiply the state itself, plus the matrix which multiply the input. We will consider now this in detail. This means I don't want to tell you anything about that, at least through this slide. We will see real in detail in a few minutes. And then at the end, I will come back on this, even though I don't want really to be boring on the system here. If you consider the axis on the upper part, it's exactly in our Segway system. Here's a little bit complex, but I will show you not in detail the model, probably, you know. I would like to just emphasize some aspect and control. But if you think about this system here, which we will see now exactly with the simulation, and this system here, we can recognize that if I fix, let me say, the car, this moving mass, MFZG, the moving mass, if I fix here, is exactly this. It doesn't matter if I consider the axis in the lower or in the upper part. In the upper part is exactly, we will see the Segway. I think you know the Segway. We will see together. The model is a little bit more complicated because we have a composition of two movements, and rotation movement and let me say, in a linear movement. Therefore, we have the centrifugal force, we have the Coriolis force, we have everything which I told you at the beginning, which I don't have really time to go in depth on the model, but we will see in the context of the control what changes. What changes. Let me see if I forgot to say something. I don't think so. Let me come back. And then I will switch on the lateral camera. No, I don't think so that I forgot. It doesn't matter now. Let me, if I forgot, we will see later when I will reconsider. But the second example, again, I try to uh, clarify more conceptually some with the calculations, because in particular with Zoom in online is really, it's not difficult, but boring in any case. But we will nevertheless, we consider with some interesting aspects in control. Look at this. Let me consider just a part of the segue, no? Even though in the segue, the axis is in the, or this pendulum is in the upper part, no? Is in the upper part. Something like, something like this. Or something like this. We will go ahead slowly now. Yeah. You remember I told you the torque is generated by actuators. Think about that here in this point, I can consider a possible actuator, an electrical actuator, uh, which at this moment, if I put the actuator, oh, this is really complicated structure because I have to consider not only the model of this mechanical system, but also the model of the actuator, which consists of rotor, coils, everything which is in a motor, an electrical typically is an electrical motor. This means we have to consider not only these two energies, I will come back on the concept of energy, but also the energy related to the actuator. Forget it at this moment, the actuator, let me concentrate as an input the output of the actuator. The actuator generated torque in this configuration. Before, a possible actuator, the linear actuator, generated force. Here we have an actuator which generated torque. We consider just the torque. This means in this kind of system characterized by alpha, angular position, with its orientation, positive orientation, which is typically, but not necessarily, but it's easy to build the balance if the orientation of the input is the same with the orientation, the same, in the sense, in the same direction of the orientation of the, in this case, of the angular position. We will see why is important the angular position. As before, no? We have the position of the masses. Anticlockwise the positive direction. Then we have alpha dot as angular velocity, m is the mass, about t I already told you, g is the gravitational acceleration, b again is frictional coefficient, which at this moment we are considering everything in terms of friction forces linear. We will see in the model. M multiplied g is the gravitational force. J is m multiply L square, the inertia. Then we have the length of the arm, no? The length of the arm. Look, why I'm considering here alpha derivative? As before, I didn't tell you before because you remember I consider x and x derivative, x1 and x1 derivative, and I consider x2 and x2 derivative. You remember in the final representation, we have four equations in which we have four variables. Here we have two variables, again, position and velocity, because we have just one moving mass. Rotational movement, but one moving mass. In the example of before, we have two moving masses. Therefore, I consider position and velocity of each mass in order to describe what the energy which plays a role in the system. Here, remain on this case here. We have here potential energy, kinetic energy. This kinetic energy can be nevertheless uh, demonstrated, probably you know, is the integral of the power. Anyway, I don't have time really to demonstrate this. Also, this one, I don't have time, but intuitively, depends on the position of this. And this position here, the potential energy is zero, and then is increasing in this direction. Basically, is proportional to L multiply sine of alpha, no? Which is this distance. Anyway, probably you know better than me how we can demonstrate these equations. But very important for us in control, in the description of this mechanism or robot, let me say, which is in a part of our final goal, this segue, basically is the representation of the energies, potential and kinetic in the system here, as a function of alpha position, as a function of the velocity, angular velocity, angular position distance. We say that these two variables are the state variables, and they are, as I told you, now connected with the internal energy, because we are considering this an external energy. About internal and external, sometimes we have a different interpretation, but in any case, depends. If I put zero this input, this external input, nevertheless, I have energy in the system, consider its position and its velocity. This is a little bit the concept of internal energy. We have a different interpretation. Be careful. No? Look at this now. This is the balance, the Newton balance. I didn't use the Lagrange approach. I think here is more intuitive to consider this balance. Consider this is basically the inertial force or torque because of the rotational acceleration. The inertial torque, which is equals the input torque minus two torques. As I told you, the linear friction torque, in accordance with what I told you, the linear friction torque. And this is the, let me say, potential torque, which is an energy. The torque is an energy, joule. I don't know if you remember. B is positive. Already defined the state variables, alpha and alpha derivative, because we have a correspondence, let me say, between position and potential energy and vice versa. And angular position, they are again angular both, and kinetic energy and vice versa, because of this. The idea is to describe the model in terms of energy through variables, position, angular position, and angular velocity. Again, let me change a little bit the notation, because in some books in control, typically we consider alpha 1 and alpha 2, in which alpha 1 is the position and alpha 2 is the velocity. This means if alpha 1 is the position, alpha 1 is equal alpha, in accordance with the notation which we are using until now. In accordance with the notation which we're using until now. And the derivative of alpha 1 is equal to alpha 2, the velocity. So we use the notation in control, which means the derivative of alpha 1 is equal to alpha 2. It's basically in a kinematic expression. This means the derivative of the position is equal to the velocity, in accordance with what I wrote here. And the derivative of the velocity, which is the acceleration, very important acceleration, it depends on the system. This means it is enough to explicit this expression, because alpha dot dot, in our case, is alpha 2 dot. This is the acceleration. But if alpha 2 is the velocity, alpha 2 dot is the acceleration, which in our specific case equals this expression here. Why this representation is familiar? in control, we will see that the idea to control a system is always to control the energy. But if you remember in high school or in physics or in technical mechanics, in this case, technical mechanics, for the energy, to represent the energy, to describe the energy of a system, means to describe the changes of the energy. I don't know if you remember. I don't have time to go in depth on this, but um, probably you know this. No? This means if the energy is characterized in one case of alpha 1, in the other case of alpha 2, which is the derivative of alpha 1, no? Alpha equal alpha 1. Alpha 2 is the derivative of alpha 1. This means I can write in this form here the changes of energy in equivalent form. Because again, we have a correspondence between potential energy and kinetic energy. And here, in accordance with this position here, we have the changes because the derivative, you remember in high school, the derivative or the derivatives represent, in the plural, the changes. Now, this is a little bit the idea. Very important now to look at the definition of equilibrium point because we are in the presence of a nonlinear system. And also in control, or at least in control of a nonlinear system, to localize, to identify the equilibrium points allows really to evaluate, let me say, the control in general. Let me show you some theoretical parts. Let me consider t equals 0. This means without input, where I can see the equilibrium point of the system if I don't have, if the torque is 0. We say autonomous system. The definition of equilibrium point are characterized by no changes in potential energy, no changes in kinetic energy. Equilibrium makes sense. This is definition we reflect as an intuition. If the changes represent our dynamics, when the dynamics equals 0, we have points, when this happens, which you can call equilibrium points. Now, from the first equation, we have this. Alpha 1 derivative equals 0 implies alpha 2 equals 0. Easy. If alpha 1 derivatives equal 0 implies that the velocity is equal 0. This means we are already in a condition from alpha 2 in accordance with the definition, or a part of the definition. Alpha 1 dot equals 0, when basically the potential energy does not change, the derivative is equal 0, we have alpha 2 equals 0. But now, if alpha 2 equals 0, we have alpha 2 derivative equals 0. This is 0 from the basic definition. This is 0 because this is 0. We obtain from the second equation, which is written here, that the condition on alpha 1 to calculate the equilibrium points is this one, 0 equals sine of alpha 1. This means sine of alpha 1 equals 0 implies alpha 1 equals k multiplied pi. You are better than me, I think. I'm sure about that in math. For k equals 0, equal 1, and so on, no? Because it's in a periodical function. No? Periodic with respect to pi. Yeah, I remember well. But of course, practically, we have just two equilibrium points. Alpha 1 equals 0, alpha 2 equals 0, this one, for k equals 0. And this point here, up, down and up, for k equal 1. The rest is periodical. I will, for k equal 2, again, this one, for k equal 3, again, this one. Basically, for even k, we'll obtain always this. For odd k, we'll obtain this one. Basically, we have alpha 1 equals 0, alpha 2 equals 0, alpha 1 equal pi, alpha 2 again equals 0. And then we will repeat mathematically. But physically, we have down and up, or up and down. Let me mimic if I can. We have this position as an equilibrium point, excuse me, this position, no? Equilibrium point. Why you can see this in the red column? We will see that the analysis of the equilibrium points are important in order to evaluate possible control, not only at the equilibrium point, but everywhere, everywhere. Out of to control this point here, it's more difficult to control this one. It's more difficult to control this one because here we have to works. We have to, excuse me, to work against the strongest moment, no, of the torque, or natural torque, because it's mg multiply L. Let me go ahead. Let me introduce quickly to theorems. If you want, we can take in probably is better rest very shortly. I would like to say 10 minutes, and then I will present two theorems which we applied and let me say in control. Then I will do the calculations and then I will simulate. Let me take 10 minutes because I have also to call. So we relax a little bit because we need a little bit force, let me say force. To this theorem, I don't do the demonstration, but intuitively I try to explain. And then we will see with Simulink, after some calculations on the system here, how we can apply concretely in the Simulink. It's already an experimental setup. No? I come from industry. I didn't tell you, I come from industry originally. And everything which we realize in real products, in robotics, in control for robotics, is first of all simulated in Simulink MATLAB, and then we use some hardware in the loop. And just at the end, we implement for prototyping and so on. Give me 10 minutes, so I call, we take a small rest. Let me say we will restart more or less half past. And so we try to have energy for these two theorems and which we would like to apply in this robotic system, even though basic robotic system, but nevertheless, my professor in Santa Barbara, I studied in America, say without background, we cannot do any advanced applications. In the meantime, I recall send me an email with your ID and group 2 if you not did yet. 10 minutes and we'll come back. Okay, now let me introduce quickly, without demonstration, or demonstrations, no? Because I will introduce two theorems. Extremely important in robotics in general. And then I try with this relatively easy example, we will see that in the application, it's not so easy. I mean, it's not so immediate, I would like to say. Let me switch. But the idea with this lab in this form, in online, the idea is to understand the basic knowledge, which can be applied also in extremely complex robots, let me say so, in control, I would like to say, no? Because again, in the application, in lab, without controlling, we cannot use. Until now, we localized, or we identified, I would like to say, we identified two equilibrium points characterized by these two value of the state, alpha 1 equals 0, alpha 2 equals 0, practically, let me say, position down. and alpha 1 equal pi, and alpha 2 equal 0, position up. It's intuitive, no? In accordance with the notation, in accordance with the initialization, in accordance with the orientation, excuse me. Now, the theorem number 1 is a theorem which allows to classify which one or which equilibrium point is asymptotically stable, which is stable, which is unstable. Classification of equilibrium points. This is important in the control because allows to say which position, in this case, or which trajectories, we will see the differences. The difference is more difficult to be controlled. And it allows to say sometimes in more advanced analysis which kind of controller or control strategy can be applied. Let me consider the following dynamical system. Quite abstract, but look, x is in a vector. We can see for this underline, the derivative of the vector is in a function of the vector and the input. Exactly what I told you in the presentation, exactly what we have here. The derivative of the state vector, which consists of two components, alpha 1 and alpha 2, the vector, the derivative is alpha 1 derivative, alpha 2 derivative, as a function of the state alpha 1 and alpha 2 and the input t. Now, in the slide, we have seen that everything can be written in case of the linear system in terms of matrices and vector. Here we have a field because we have a nonlinearity is here. Sine of alpha 1. Sine of alpha 1 is nonlinearity, is not a sine, is not a linear function. You remember, we have seen in math. Let me quickly explain the theory. Here we have basically, again, a model. Let me say nonlinear model, even though the theorem holds also for a linear model. Then in the vicinity, in the close to an equilibrium point, x0, we say that the system is asymptotically stable if all real parts of the eigenvalue of its Jacobian matrix J, calculated at 0, have strictly negative eigenvalues, no? Real part, clear. If at least one is positive, this means that the equilibrium point is unstable. The theorem closes with this sentence. If the eigenvalue of real part or at least one real part equals 0, then no conclusion. This recall us the linear system, but if I emphasize again the word or the wording, then in the vicinity, close, but this recall us the linearization, not only this word here. Also the Jacobian, I don't know if you remember in math, the Jacobian is the matrix of the partial derivative. Now we will see with the example. This means we can very well interpret this theorem here. If everything is, the real part is negative, is asymptotically stable. If not, depends on the cases, at least one is positive, is unstable. If one is negative, if you have also 1, 0, we cannot conclude anything. No conclusion. No conclusion because it's an approximation. Let me say so roughly interpreted the last sentence. Let me look at the theorem 2 and then we will go ahead. We will go ahead with the application at with our case. Again, the system. This is, let me say, a little bit more important, but also because it's more constructive. The Friese theorem can be used to classify. Classification, nevertheless, is important to choose the strategy, of the to control. But let me go ahead, then we will see. We discuss again everything more in detail with the case. Look at this. An equilibrium point. Now, the system is the same, non-linear system, but the theorem holds also for linear. Because a linear system is a particular case of a nonlinear system in which the nonlinearity elements are not present. An equilibrium point x0 or trajectory x0 could be also a trajectory, very interesting. I can control also a motion. Do you remember at the beginning I insisted on this wording, motion? Could be also an emotion, a trajectory. Motion, trajectory, we consider a synonym in this sense. An emotion or trajectory in a set of points is asymptotically stable if there exists a positive defined function v of x, just to understand what I intend from positive function, for x0 in the domain. X0 basically is the point which we want to consider. I mean, in the vicinity of D of x0 or f of x0, such that v of 0 is equal to 0, or the all points if you consider a trajectory equal 0. D is the domain. D is the vicinity. Could be also better formulated, but I think you understand what is x that is in the vicinity of x0. Yeah, it could be a little bit reformulated, but anyway, close to x0, we have something like that. Of course, if this condition is valid everywhere in all D, not only in the vicinity, of course, we have a global positive definition. It could be improved this. But anyway, let me go ahead in the application. At x0, the x0 as in the function of time, the trajectory must be 0. If I find this function, and if the derivative of this function at x0 or in the trajectory with the derivative at x0 of the trajectory is equal to 0, we have this point of this trajectory is asymptotically stable. This means I can remain at x0 or I can track x0 of t. It seems to be complicated, but now we will see the applications and then we will come back on this formulation. It can be a little bit improved, of course, yeah. But I would like to concentrate on the application now. So we can repeat this page number 3. This means I have to look for the page number 4, which is here. Application of theorem 1. We have 2 equilibrium points characterized by these 2 conditions. Now, please calculate the Jacobian. Now, I put for you the definition of the Jacobian because it could be that you don't remember. Again, T of t equals 0, autonomous system. I am looking for the equilibrium point of the system without input, or the inputs if I have more than one. This is our system, which can be seen in our case split in two parts. Do you remember? Alpha 1 derivative, which is x1 derivative, equals alpha 2, which is our f1. And then we have alpha 2 derivative equals the relative complex expression. What is the Jacobian of our system? Is organized, you remember the Jacobian is the matrix, if you remember math, of the partial derivative. Here we have the derivative of f1 with respect to alpha 1, excuse me, the derivative of f2, the derivative of alpha 2, which is this here, with respect to alpha 1, we have the derivative of alpha 2 with respect to alpha 2 itself. And here it's quite similar. This expression, the derivative of this expression with respect to alpha 1, and here we have the derivative of this complex expression with respect to alpha 2. Let me see what happens in our case. Again, this is f1 as a function of the state. We have just alpha 2. This is f1 as a function of the state, which you have in this case alpha 1 and alpha 2. Look at the Jacobian. Why 0, 1? Because if I do here, the derivative of alpha 2 with respect to alpha 1 is 0, because alpha 2 is not alpha 1. If I do here the derivative of alpha 1, which represent my f1, with respect to alpha 2, the derivative of alpha 2 with respect to alpha 2 is 1. What about this? Easy. It's the derivative of this expression with respect to alpha 1. You know that the derivative of sine is cosine. The variable to be considered is alpha 1. Why this? Because you have to do the derivative of this expression, f2, with respect to alpha 2. This means this is 0, it remains b divided m L squared. Now, if you remember the theorem 1, which says that I have to consider I have to evaluate the eigenvalues of the Jacobian at the equilibrium points, this one and this one, I have to calculate the eigenvalues of the eigenvalues lambda, excuse me, of J, which can be calculated with this equation. Probably you remember from math. In our case, we don't have to recall everything from math because we can use the knowledge of the tool of MATLAB or different tool which we can use in robotics. Anyway, we are here from the lab. It's easy to recall the equation. If you don't remember, it does not matter. But this is the equation which allows to calculate the eigenvalue of J, this matrix here, the Jacobian. Jacobian is a linearization. Therefore, the theorem says the eigenvalues. The eigenvalues characterizes always in a linear transformation. Determinant of this. Let me drink something because I'm not able to speak. Is this expression. Now, calculated at the first equilibrium point. First means this condition. We have this expression here. If you remember the Cartesian theorem, these eigenvalues and at the real part negative. I don't know if you remember. If you don't remember, you can calculate. Please remember that B, M, L, G, and L and G are positive. No? The real part could be also complex, but the real part is negative. The theorem says that this equilibrium point is asymptotically stable. It was already intuitive because alpha 1 equals 0, alpha 2 equals 0 was this one. This means if I am moving around this point in the vicinity close to this point, I will come back to this point. This is the concept of the asymptotical stability of a point. If I have a trajectory, it doesn't change much. But of course, I didn't consider now the trajectory. Because the trajectory is more important in controlling the second theory. It's intuitive. No? Let me mimic. We are not in the presence in the lab. This means this equilibrium point is asymptotically stable because if I move a little bit from the equilibrium point, I will come back to the equilibrium point with oscillation, without oscillation. Depends if I have the eigenvalues positive. If I have eigenvalues positive of, if I have a complex or not complex eigenvalue. With complex eigenvalue oscillation, let me show you what I intend. Excuse me, yeah, let me see this. With complex eigenvalue, have an oscillation. Yeah, it seems to be we don't have a complex eigenvalue because of the strong friction. Huh? But probably you know better than me, no? This concept of the complex eigenvalue with oscillations in the dynamics, not not convex eigenvalue without oscillation in the dynamics. Of course, this depends of many things. Some things, many in the sense depends. Let me show you quickly. On B, M, L, G is given because inside the root we have this square minus 4 times G divided L. This means this part here square must be larger, less than 4G divided L in order to have oscillations. And then we can build conditions on this element here. Typically, no, we have a condition on, we can see on B, M, and L. No? But this can be easily calculated. Let me check the second equilibrium point. This is the second equilibrium point, the equilibrium up, let me say, the upper part. This was the determinant, which is, if it's calculated at pi and 0, we have, instead of, do you remember, plus J divided L, at pi, we have minus J divided L. This means one eigenvalue at real part, positive. If you remember Cartesio rule, but if you don't remember, you can calculate. Let me see if I forgot. Because do you remember the Cartesian rule? We have a plus, plus, minus, minus. Huh? Okay, this means that this upper part is intuitive, of course. This this equilibrium point in the upper part is unstable, because we can demonstrate that one eigenvalues is negative, is positive, excuse me. As I told you before, the oscillations depends on this element. You remember in the under the root, this squared, and then 4 times this multiplied this. No? But it's not relevant in terms of stability or asymptotical stability of the equilibrium points. But here is relevant the real part. Here we have, if you remember Cartesian rule, otherwise you can calculate exactly the expression of the two eigenvalue lambda 1 and lambda 2. We have one eigenvalue positive, real part, no? Excuse me, real part. Now, let me apply it now here. The control exactly at this point here, at this unstable equilibrium point. Before starting, nevertheless, let me recap why this analysis. We can see it is intuitive, but if you have a robot complex, if you have a robot with more elements, of course, this is in the project. This is something which could be considered in the thesis. The equilibrium point, or their stability, and the analysis of stability allows to say that to control this equilibrium point here is more difficult than to control this equilibrium point is more difficult than to control this equilibrium point. It's intuitive. More difficult in, of course, depends with the same specification. With the same specification. Also, this equilibrium point could be complicated, but if the specification are the same, specification means the goal. Of course, this element here required more, let me say, energy, no? Because if I'm going a little bit far away, I have to work against a moment which works again. This is a little bit the idea, because this point here, if I want to stabilize this point here, is for its nature asymptotically stable, assuming that I want to remain at this position. I want to remain at this position, and I have disturbances. Of course, this is more difficult than this one. I put this red here because I told you I can also stabilize here. I can also stabilize this point. And also this point, because it's equidistant from this equilibrium point and this equilibrium point, it's extremely difficult. I would like to say conceptually, practically, more difficult than this one and more difficult than this one, because nevertheless, these two equilibrium points are equilibrium point. This is not an equilibrium point. This means for its nature, this point here, that this position tends to go far away. This means here I have nevertheless act, I have nevertheless do something to maintain this position. We will see now how I can apply the second theorem to maintain, for instance, this upper or the equilibrium point at pi, characterized by alpha 1 equal pi, and please not forget alpha 2 equal 0. When I will simulate later, we will see how change if I want to yeah, control this, or if I want to control pi, alpha 1 equal pi, and alpha 2 equal 0, or if I want to control alpha 1 equal pi divided 2, and always alpha 2 equal 2. Of course, in this position here, always alpha 2 plays nevertheless in a role, but alpha 2 equals 0 characterizes these two. If alpha 2 is not 0, we don't have equilibrium points. This must be considered. Alpha 2 equals 0 is an important condition. No velocity at this point and at this point. No velocity 0, to be precise. Velocity 0. But let me repeat everything with the simulations. Before starting with the simulation, let me show you what I intend. You remember the theorem 2 says that we need to define an Lyapunov function candidate. I didn't insist on this nomenclature. And Lyapunov function is a function which guarantees all the property of the theorem. This means assuming that is a candidate. It's a candidate because it's positive. About k equals 0, I don't have much time, larger than 0. I don't have much time to insist on this, but we will see later, eventually, in a word on this condition here. Let me at this moment consider this. Because for the positiveness of V, we don't need k equal larger than 0. We can see, no? because everything which is here is squared. This is positive. At pi and 0 is 0. This means two conditions are satisfied. Is positive because everything which is inside is squared. For this condition, I don't need k larger than 0 because it's inside. Now I have to find a torque which must be realized with an actuator. This is, we will see, this is also in the project. No? If I consider an actuator, the system is extremely more complicated because I have to consider also the state variables of the actuator. Let me forget this because it's already complex here. No, we will see with the simulation. Now I have to find t of t such that the derivative of v is less than 0. Please pay attention. Dot means the derivative with respect to the time. Close to this point, but basically we can consider also the whole domain if you want to stabilize everywhere. Anyway, we will see. The theorem says close to this equilibrium point. Please, the equilibrium point is characterized by both conditions, alpha 1 equal pi and alpha 2 equal 0. We will see this is automatically guaranteed, or almost, let me say. Let me say so, and let me show you what I intend. Now, instead of this long expression, I typically, we consider this expression here in which S is exactly, you remember what we have before squared. Now, let me calculate the derivative. 1 divided 2 is there just formally, and we will see, we can, if you don't like, we can omit this. But it's there because concerning the positiveness, doesn't help, doesn't change anything with and without 1 divided 2. But the derivative means 2 divided 2. No? This means we can forget this divided 2. But in some books, they don't put 1 divided 2. But I, in the mostly, we can consider because we have in this sense this simplification, but it's not trivial. This means the derivative of this expression with respect to the time is s 2 times s divided 2 multiply s derivative. The derivative of the function x with respect to the time if x depends on the time is exactly here. S, which multiply this, because S derivative, which is here, is this expression here, which I can write in this form. Now, instead of alpha 2 derivative, here, instead of alpha 1, is not visible, but it's alpha 1. Is alpha 1 of t. It's not very well visible. If you want, I can improve a little bit. Because came from here, no? Pi is 0 when I do the derivative. Now probably it's a little bit better, no? We have here alpha 2 derivative plus k multiply alpha 2. Hmm? Alpha 2 is this expression here from the model. I will plug in here, and I will have this expression. And then to obtain alpha dot less than 0, first of all, I will cancel. We can see here, cancellation terms, everything which I have here with a particular t. This part in some literature, we find a way to proceed. We call this equivalent part. But of course, I have the derivative equals 0. It's not exactly what we want. But if I add now this element here, I will obtain the results because inside the parentheses here, thanks also this cancellation, which basically is irrelevant, but I would like to put it nevertheless, I will have eta with eta positive, which multiply s, which multiply sgn of s, which equals minus eta positive, absolute value of s of t, which is negative, if as long as eta is positive. What is this? Now, of course, why this is 0, the derivative of v at this point? We can see from here. Because this is 0. Huh? Now we can make a little bit on this. In 1 minute. Let me assume that it's at this moment is 0. What is SGN? SGN is this function here. I'm closing. Huh? The sign of S of t is 1 if is S of t is positive, is 0 is S of t is 0, is minus 1 is F of t is negative. If you remember, this is a sigmoid function. It can be represented in this form. Can be represented in this form. But if you remember, x multiply SGN of x is absolute value of x. In our case, our x is S of t. Therefore, I told you that if eta is positive, we are always negative. Now, before closing, I am almost ready. Let me think if I forgot to say something in this context here. Yeah. You remember, I told you that this must be assuming that is 0. When I say assuming that is 0, I told you this at point pi 0 is 0 because of this. But I forgot with intention to say that this is going to 0 around pi, pi 0. The concept of the surrounding is always in a concept which must be considered when we have to do with the derivative. You remember, the derivative is always defined in the concept of the surrounding. This means this is 0 in the surrounding of pi 0 if this element here is not infinite. Try to think that I am moving in the surrounding of pi 0. This means alpha 2 is moving the surrounding of 0. But this is valid, with better to say, this is valid just if I demonstrate that this dynamics is limited, but it's limited if k is larger than 0. This means this k larger than 0 must be given. Now we clarify everything. K larger than 0, eta larger than 0, because we need at the end this v derivative less than 0. And this is valid, but we have to say that k is positive. Otherwise, even though this is tend to 0 when we tend to pi 0, but what about this? This is limited if k is positive. This means we have to say k is positive. The last consideration, let me see if I forgot to say something. I don't know. When now we simulate, now we go until the end here, we take an rest very shortly, and then we simulate. The simulation will be, I hope, a little bit easy. But you realize, even though the system, it seems to be quite simple, this robot, the mechanical system, you realize that in order to be controlled, it's not so immediate, the theory or the element which I have to consider. We will see now in simulate. The last question, how robust is this method? The reason is why I'm speaking about robustness. Robustness means assuming that I don't know exactly the parameters. I don't know exactly B. B is really difficult to be estimated, the friction. M, oh, I can wait, no? L, I can measure, but anyway, I cannot be totally precise. But in particular, B, I told you that B is just a simplification of the system. It's just really a simplification of the system. Now, of the friction system, of the friction model. Let me consider that the cancellation is not precise. Remains inside the parenthesis something, delta, I don't know how much, but of course limited, I assume that it's limited. That I can consider disturbance. I can consider disturbance as is acting on the system. But if eta is larger than the maximal value of this cancellation error, is larger than the maximal value of D, of course it's a conservative hypothesis, but it happens, it's easy to see, that we maintain the negativeness of V derivative, because if this is eta is larger than the maximal value of this delta, assuming that is limited, the maximal value of D, this element here is always less than 1. It's always less than 1. This means if S of t is positive, this means this is positive, or better to say 1. This means this minus this is less than 0. This is positive. This means the derivative is less than 0. Yeah. What happens if this is negative? If this is negative, this is -1 with minus is +1. Is +1. Nevertheless, independently of the what happens here, this is always positive. No? I mean, excuse me. This is always positive, independent of the signal here. We cannot overcome this positiveness here because this is always between -1 and 1. Always between -1 and 1. This means you cannot overcome this one. This means here inside remain positive. But this was negative, no? In accordance with our second hypothesis. This means this is negative. No? I don't know, if you want, I can repeat this concept here. I can repeat in the sense that if S is positive, this contribution is -1 because SGN of something positive is 1 with -1. This element here, independently of the sign here, it's better to explain so, is always between -1 and 1. This means cannot overcome this negativeness This is positive. Uh, the V derivative is negative because this is negative and this is positive. Similar consideration I already did uh, if S of t is negative. This means we have a plus 1 here, but independently of the sign here, it's always between -1 and 1. This means we cannot overcome the positiveness. This means everything this is positive with something negative, we have always that at the end, excuse me, here, you have something negative because this, is positive because of the negativeness of S of t. The last consideration is what is this SGN? Again, I told you that SGN can be graphically represented in this form. Sigmoid function. It could be often could be the problem to be applied because the function which I have to implement in this control is not a continuous one. Could be very often the problem, practical realization, because we have to switch. Eta could be also very large. To have an actuator, we switch between two large value is not so too easy to be realized. It probably is expensive also in terms of costs. Very often we used an approximating function. Here we can see here 2 divided by arcotangent of gamma S of t or hyperbolic tangent of gamma S of t. Gamma is something which allows to approximate better, to approximate the SGN. Increasing alpha 2, we can see larger than alpha 1. We approximate better and better, increasing alpha, this SGN function, this ideal sigmoid function. Okay. Let me now take rest, 10 minutes until I that as before, and then we will open MATLAB to repeat, to apply this control law, which consists of this cancellation term and of the minus of algebraically plus this switching part to stabilize, for instance, the point pi 0 or pi divided to 0, and then I will give you as an exercise to stabilize any trajectories around. Anyway, any trajectory, I would like to say. This means any motion of this inverse pendulum. Okay, let me take a rest again a little bit. 10 minutes. And then we will come back to show you the simulation to discuss something in this contest. We will see in 10 minutes. Okay, we have seen many things. Now we sum up everything with Simulink. We repeat in this sense. And then we conclude this lab fleshing out a more complicated system. But of course, we have seen that also within the relative simplified situation, we have nevertheless, I would like to say, quite complicated expressions, or the method to control is not so immediate. Therefore, the structure of the lecture in this sense, in this form. Okay, let me open MATLAB and let me share. You know MATLAB, but in any case, let me quickly a little bit repeat some concepts. The structure of MATLAB very, very quickly. I mean, if you click twice on the icon of MATLAB, you can open the software, the tool. It looks like something like that. I mean, we have this, let me say, four parts. Here in the middle, in the low part in the middle, you have the command window. We can be seen uh, possible part in which I can put some comments. For instance, 1 + 1 = 2. A and S is the variable or the parameter or the result answer. No? We can see here on the right part in the workspace in which we have n A and S equal to the variable is ah, excuse me, its value together with other elements which is there because I run this program, this M file, and we can see a pendulum data. Let me um, send you directly this file per chat, and then you will find also everything in the WeCamp. So you have already. I think you received. Yeah, of course, here this M file can be used also to build complex control systems, complex functions on. Here is just used as a data file. No? We have the gravitational parameter 9,81. The semicolon means just don't show the results in the command window. Basically, it's not so extremely important function of the semicolon. B25 is, as I told you before, is the friction coefficient. K10 is important positive. I clarify why. Because in order to guarantee that V derivative equals 0 at the point, I have to guarantee it at the point, around the point, around the point. I have to guarantee that, yeah, that not only this is, let me show you here. Not only that in the close to the equilibrium point, this is 0, but also this one is not infinite. And this is not infinite for K positive, because alpha 2 is moving around the equilibrium point. And this differential equation must be asymptotically stable, or at least stable, or at least stable, in order to guarantee that V derivative at the equilibrium point is equal to 0, as in the theorem. Let me come back here. Yeah. Un eta positive for similar reason. Oh, let me come back again. Similar. Yeah, because we have to guarantee that the derivative is negative in the around again of the equilibrium point. This means for these two conditions, this negative eta must be positive because of this minus here. For this condition exactly 0 at the point, K must be positive. I clarify again. Okay, let me open Simulink now. Let me share. Now let me send, not to share in this sense, in through the chat. Let me use the chat a little bit better. Excuse me, I need 1 second. What is the chat now? Yeah. Okay, now you have in the chat also the Simulink file. Let me open the Simulink file. Let me share. Let me open the Simulink file and let me share it. Okay. Okay, let me show you here. Here, it seems a little bit confused because I put everything in one structure. Because sometimes if I put the model in a subsystem, the controller in the subsystem, I have to click left, right. It seems to be a little bit confused, but in my opinion, it's better than to split in some subsystems. I mean, look, here is alpha 1, the position. We can see a little bit later where this could be considered a disturbance, for instance. Here we have alpha 2. Why we have alpha 2? Because the integral of alpha 2 is alpha 1. If I know the initial condition of alpha 1, we can be seen here inside. I mean, if I go here inside and I share, where is now? Yeah, here. We can see that I put an initial condition for alpha 1, pi divided 2. This, let me say, particular initial condition. If I know the initial condition of alpha 1, if I do the integral of alpha 2, I have alpha 1. Remember in math, no? The integral of the velocity is equal to the position, angular in our case, angular position, angular velocity, if I know the initial condition of the angular position. Let me close the telephone. Yeah, and the same here, no? What we have here is the derivative, the acceleration. This means the derivative of alpha 2. Alpha 2 is the velocity. Let me, yeah. Now, look at the model. We have here an element. We have here another element. Here is G divided L, which multiplies sine of alpha 1. G divided L minus, no? Let me see. Problem is it's difficult to put here. Minus G divided L sinus. And then we have also this one minus B divided ML square multiply alpha 2. Let me show you what I intend. The model is here, no? Let me, yeah. By divided ml square with minus multiply alpha 2, and then minus G divided L sinus alpha 1. We can see that the torque, which must be implemented as the output of the controller, is divided by ml square. Let me show. Then I justify this element, I justify this element. Yeah. And the torque, we will be here. Now we will show you some elements of the torque. It's divided by ml square. This is the input, no? Divided, excuse me. This is the input divided, T of T divided by ml square. Here I disconnected this because I told you just a little bit about a possible, do you remember static friction? It's an impossible static friction. Do you remember I told you we have a coefficient that is not necessarily B divided ml square, multiply sine of the velocity, angular velocity. Do you remember this? Static friction. If you want to test at home, does not change much. Because do you remember the control law is quite robust with respect to something which I don't know exactly. I mean, theoretically, this element here should be also considered in T. I can show you. Yeah, T does not consider uh, this static friction. Nevertheless, it works. If I have eta large enough. Let me check, for instance, some aspect here. Look, this element here is also a disturbance, which is go inside the system, which I not considered in T. But nevertheless, if eta is large enough, I demonstrated that the control is quite robust. Look here. It seems to be that I would like to control here pi divided 2, but let me write pi. So we have seen exactly. But I can control any position. I told you, any position. Look, alpha 1 minus pi. This is the coefficient k, even though we say k multiply 1000, because students ask me about what happens if I increase k, which is go inside here. The position to be controlled is pi and alpha 2 equals 0. This means alpha 2 minus 0 is alpha 2. Multiply eta, multiply hyperbolic tangent. Excuse me. No. This is it's not eta. This is gamma. I made a mistake. This is gamma. Eta is here. I show you. I made mistakes in the sense I forgot. Which we can see eta, and then if you look, this is it's not exactly eta. Is eta? Let me say in the mathematical aspects. Let me show. Let me look. Where is this? Is eta multiply ml square? Let me go out here. This element here, which is in a part of T, which is in a part of T. I don't know if it's visible. No? Excuse me if I forgot, what was gamma, it was eta. Gamma is the argument of hyperbolic tangent. Which is before the hyperbolic tangent, because it's the argument of hyperbolic tangent. Multiply S. Let me show you. This is gamma. Very large value, relative large value to approximate very well the sigmoid function. And this is going here with minus. And you remember minus eta multiply ml square SGN, or the approximation of SGN. And then I have many other elements. Try to do at home, for instance, this plus B multiply gamma 2. Excuse me, alpha 2. I don't know if I shared. I hope I shared. And I didn't share. Excuse me. Now, again, I will repeat again. Here, we have exactly what ml squared and the approximation of sine. Multiply eta is here. Here inside, I told you we have eta multiply ml L squared, everything multiply hyperbolic tangent of what? 5000, which is our gamma, as I told you now, which multiply S. This block here, you can find everything in MATLAB under math operation or under common use block. If you go here inside, let me show what you can find this block, common use block, or in math operations. Let me go ahead. I told you about another elements, but check at home if you want. For instance, this is easy to be checked. Plus B multiply alpha 2. Let me show you. I don't know if I shared. I didn't share program. I hope that you see Simulink. No? You don't see Simulink probably. You see Simulink. This element here, as I told you now, is B multiply alpha 2. Why this? I need this. Plus B multiply alpha 2. Of course, you can recognize if you have time at home, all elements. This I show you, this I already told you because it's the more complicated. But look at this if you want. But you can look also this one. You can look also this and this in the control law, which I have to realize by an actuator or the using actuator, no? For instance, this G divided L with minus multiply, as I told you before, sinus of alpha 1. The other element is here. As I told you, K multiply ML square, which multiply alpha 2. Excuse me, G, no? Let me see. Yeah, K multiply M multiply L square multiply alpha 2. Exactly. K multiply M multiply L square multiply alpha 2. No, alpha 2 is here. We can see a K multiply M L square multiply alpha 2, which is here. In accordance with the MATLAB rules. It's here. Yeah. This element here. Try to do at home, you can recognize everything. Let me show you the simulation, and then we will conclude with a more complex example, but without doing in detail the calculation without simulation, because it's really a heavy exercise. Yes, could be an error, no? Could be an error, it's a disturbance. But we do without disturbance. Let me show you what happens. A disturbance which is going as a constant disturbance, which is going to disturb in this sense, let me say, here we have the angular acceleration. We can also consider disturbance in terms of torque. It's equivalent. Let me show you what happens. With some oscillations, we can also manipulate K and eta to reduce the oscillations, but we will see that will converge starting from pi divided 2 at pi. I don't know if you see it. Of course, changes eta and K, we can reduce the oscillation if we are disturbed by the oscillations. Let me consider without this disturbance, with a disturbance in terms of angular acceleration. Of course, now the controller should work less, because we don't have the disturbance, which is not considered in the control law T because I don't know the disturbance. We can see that we don't change much. This means robustness. Let me show you also this. Let me put here this friction, even though it's not considered in T in the control law. We can see how robust because I considered in very high. Let me show you the robustness. Robustness means it works somehow. Huh? Let me share. To reduce the oscillations, we have to change K and or eta. Less eta, we will be we obtain less oscillation. But if eta guarantees nevertheless, also K, also K, probably more acting on K because eta, the risk to reduce eta that it could be that not guarantees the stability because eta must be large enough if we have something which we don't know. Please pay attention, the condition of Lyapunov is sufficient condition. This means if we don't find, if the condition is not satisfied, we say conditions are not satisfied, this does not mean that the control doesn't work. Let me reduce K. Let me try again, and then we will conclude. I'm not able now to switch. Let me go here. Let me go here. Let me write, for instance, K equal 1. Huh? I don't know if this is enough in 10 of 10. Would be that I have to reduce more because why I have to reduce more? Because we manipulated the K here. No? The real K before was 10,000. Now is 1,000. I don't think so that will change much. Let me show. Yeah, a little bit we can see. Yeah, this level is pi. No? We can see at 3,14, believe me. We can see that reduced. This means if I go here and I will reduce here, instead of, for instance, 1,000, I put 10. Let me show you what happens. Of course, we will achieve the goal slowly, but without oscillations, I hope. Let me show. This is what I guess. Yeah, it's not yet achieved, but we will achieve it because the stability depends on eta. The stability depends on eta. Try to do at home some modification of eta and of some different disturbances, also sinusoidal disturbance, any kind of disturbance, as long as eta overcome these disturbances, the maximal amplitude of disturbances, we don't realize many things, many differences. I mean, try to put here at home yeah, we don't have disturbance, but we can put 20. Here we can put a sinus. It doesn't matter where, also in the output. It's, of course, we have a slow solution. Now, the system realize that we have a disturbance, but somehow the disturbance is compensated. Slowly. We will converge, believe me, at 3,5. Try it with sinus, cosine. If you want. Let me conclude in these 50 minutes with a segue example without going depth, but just show you how with this Lyapunov approach, we can really run with the segue. Excuse me for, let me share these slides without again going depth on the model, because really this I need a lot of time, which exactly. Look at this. The segue in any case is not exactly this, because the uh, this arm isn't the upper part. No? The arm of a segue is in the upper part. I don't know if I can find in the picture for you in order to realize, just in a second. In any case, we can see that the model consists of course, we have the pendulum. If you block the car, the system is exactly what we analyzed this. But yes, the system is complicated because we have two movements and rotational movement combined with an, let me say, linear movement. Therefore, we have a centrifugal force. We have this Coriolis force. Anyway, it's not so immediate to build the model. It's not immediate to build the model. In any case, assuming that we have the model, no? Which consists now in 4 states, because we have 2 states for the arm or the axis, and 2 states for the arm, and 2 states for the car. Always position and velocity of the car, linear position, linear velocity, and as before, angular position, angular velocity. But the system is the combined system. This means look in the literature about this model. Let me look if I find in a picture of the segue. 1 second. Uh, Now I found in a commercial. Yeah, basically we have the arm and the upper part, and you can push ahead in order to move. Why that? Let me show you a couple of equations in order to understand what I intend. 10 minutes, 12 minutes to conclude. Segue. I copied the model. At this moment, forget where the model come from. But of course, assuming that we know the model. Otherwise, really, we need just a lecture in the lab to justify this model. Anyway, this is a complex model we have because in a combination of two movements. Therefore, we have a centrifugal Coriolis, probably you ever seen in math or in physics. If I want to control the system at these equilibrium points, believe me, I didn't calculate for you because this is so a little bit complicated, but believe me, alpha 2 equals 0, alpha 1 pi, exactly as before. This means that we have the arm at this position. But we want to control also the position of the car. If I do the calculations, very boring calculation, but simplified because we can consider Fc, Ft, which depends on the state constant. It's in a very rough simplification in order to obtain at the end this expression, and this expression here for S derivative. Everything came. Do you remember I told you at the beginning in the presentation, in the presentation PowerPoint, I have to express everything in this form here. Remember, I told you before. Derivative of position equals velocity, velocity derivative, the dynamics, this for the car, this for the arm, no? Alpha 1 dot equal alpha 2, and this the dynamics, alpha 2 dot equal this one. If I substitute, but considering this element, as I told you, FC and T and FT constant, it's not valid, but let me consider the variation is very small. I will obtain at the end, after considering this expression here, if I substitute, is exactly as before, no? Instead of x2, this expression. Again, at the end, let me go a little bit faster. I can calculate f as before, but of course, uh, it's quite boring. It's quite boring. Well, let me see if I forgot to say something. No, I don't think so. The problem is here I cannot run because I stabilize also the car. What we can do to run? Typically, we define, let me show you the last slide, an like, an Lyapunov-like function, which consists of stabilizing just the vertical position of the arm. We don't consider all states as I should. If I do so, and I, instead of alpha 2, I will, alpha 2 derivative, I will consider the expression alpha 2 derivative, dynamics of alpha 2 derivative. You remember, this is here. I can now calculate F, the force which I have to generate to move the car, in order to stabilize the position pi 0. What is the effect of this? It's very boring, but I would like just to show you the idea. The effect of this is, in order to stabilize in the vertical position, if I push ahead, the car will run. If I push ahead more and more, the car will run faster and faster because he tries to stabilize the vertical position. This means I have to maintain the angular position of the arm in order to determine the velocity. The velocity will be constant because somehow, somewhere, sometime, somewhen, excuse me, I will achieve an equilibrium between the forces, and in particular the friction force. With this position, I can control the velocity of the car because the car will run in order to stabilize the vertical position. Because if I don't push ahead, the car will be this. But of course, the idea is to run with a desired velocity, which I can determine pushing and maintain ahead. If I push really ahead, I will impose more and more velocity, acceleration in this sense, more and more force. This came, the calculation is boring, the simulation, but I have it, the project. If you want to go ahead with this, with me in a possible project, I don't know, in the master thesis, we can cooperate with your university. We did in the past. We can formulate some different problems in this context here, segue control, no? But now the idea is to show you based on this easy example, which I consider this inverse pendulum at this position, for instance. Of course, the problem in the Segway is extremely complex because we have two equations more complex because we have the combination of two movements. And then also the choice of this pseudo Lyapunov function, of Lyapunov-like function, because the Lyapunov theoretically should include all states. But if I include all states, I don't move. Because if I put here, the system try to come back on my original point. This means I have to consider the Lyapunov function which don't consider the position. This means I neglect the position. The position will be not stable because the idea is to travel. No? Again, if I don't push ahead, the system will stabilize somewhere, x1 and x2. Can move. If I have a disturbance, I can move. I mean, I put a disturbance and then try to stabilize. But if I push, the system try to generate a constant force in order to stabilize our desired, let me say, position. But this means I will travel within, at the end, steady state and a constant velocity because the force which I generate will be nevertheless somewhere compensated by the friction. Okay, let me see if I forgot to say something about the Segway. Really, if I put really all calculations exactly, if I put the implementation, this really it's not a suitable lecture at least in Zoom. Let me see. Let me come back if I forgot to say something, but I don't think so. At least the last part of a Segway, the idea was to sketch and to tell you about the Lyapunov function, the Lyapunov-like function, which can be chosen to have a control law which is suitable for our goal. The Segway is there to run, to travel. This means if I put in a full, let me say, Lyapunov function, or an exact Lyapunov function, which includes all states, I cannot travel because the system try to stabilize all state, all energy, if you want, if you recall my initial sentences. But the idea is to run. This means forget the stability of x1 and x2. x1 is the position, x2 is the velocity of the car. Forget this in the Lyapunov. Forget x1 and x2. Don't consider this. Because if I consider, I cannot travel. And just consider as a pseudo Lyapunov function, Lyapunov-like, just to stabilize the arm. To stabilize the arm, this neglecting the position of the car. This means if I maintain a constant force to maintain alpha 1 head, let me say, in accordance with I conceived in the Lyapunov function, I will try to stabilize, which is not possible because I maintain with the same, and I will travel with the desired velocity. If I increase the alpha 1, I will increase the velocity because I will increase the force, but increase the force means I increase the acceleration, but I will have an equilibrium between the forces because of the losses which I have in the system. Okay, I hope it was not boring. The last part is just to show you how the applications, also complex applications, this could be also a part of a PhD program. I mean, it depends of the of the of the specification, what we want to analyze. I think the idea was to flesh out in the lab, what in the virtual lab, what we can realize in control of, let me say, robot of the mechanisms. Very interesting, this is a segue, but based on the basic knowledge. The Lyapunov function allows to achieve the goals, because here in this case, if I don't care about x1 and x2, position and velocity, the system, the control law, which I can realize in the same way, more complex in the calculation, boring in the calculation, try to stabilize just this position if it is possible. I maintain, and then I will obtain my travel if you want. Okay, thank you for your attention. Let me close now the lecture, but I am here for questions. Thank you.